Okay, so we're going to finish up lesson 19, the last problem, and then move on to lesson 20 today. And so, because this is supposed to be like a normal class, it'll be about 50 minutes, but we'll see how far I get. I may only do half and half, but you should regardless watch 50 minutes of lecture video today to make up for the normal class. So this last one on number 19, lesson 19, says calculate the pH of a 0.4 molar solution of sodium benzoate, and the Ka of benzoic acid is this. So it tells us that this is benzoic acid, it's a Ka, so we know that in order for this to be the right equilibrium expression, we're going to have benzoic acid, which is this formula, plus water. And it's an acid, so it's going to give up its proton, and it's going to make benzoate ion. In this case, it is sodium benzoate, because this is out here in there making a compound as well, but we're not going to worry about it in solution. And it says calculate the pH of this solution. And so there's two ways to do it. We can either, one, set it up as it is right now with the ice table, because this is the Ka, or we can use the problem like this, where sodium benzoate is a base and it accepts the proton, and this is the Kb because it's acting as an acid and as a base. Okay, so two different options, and we know that we can relate the two to each other through Ka times Kb equals Kw. So if I know Ka and I know Kw, I can solve for Kb because this is the conjugate base of benzoic acid. So I'm going to go ahead and use the second one just because it's here at the bottom and I like to just not have to rewrite it. But you could do either one, okay? So in this case, water still doesn't count. In sodium benzoate, we're told we start with 0.4 molar, no benzoic acid, no OH, and the reaction is going to shift to the right to produce products and consume the reactants. Okay, so I have my equilibrium values. Now this is written in the form of a base, so the expression would be Kb is products over the reactants, but I have a few things to figure out. The first is I don't know what Kb is, so off to the side I'm going to have to determine what Kb is. So I have Kw, Ka is my unknown, and I have Kb. So, oh, I'm sorry, I have this backwards. I'm looking for Kb, and I have Ka. Okay, so I'm going to divide the Ka onto both sides, and I'm going to solve for Kb, and I'm going to get a tinier number than the Ka, which suggests something about equilibrium. The Ka value is larger, which means the reaction is very heavily favoring the products, whereas the Kb is very small, which means it's favoring the reactants. And if you look at what's on the product and the reactant side, it's sodium benzoate. So that makes sense. It's favoring the particular compound. Whether it's on the left or the right is reflected in the balanced chemical equation. Whether or not it's favored is reflected in the Ka and the Kb. So here's my Kb. Now I need to see if my 10% rule can be used here. So if I multiply this by 1,000, indeed, we're going to see that this is still, it's not right like that. This is still going to be less than 0.4, which is my starting amount, which means I can get rid of that minus x. And we're going to see most of the time that that's true, that we can ignore that minus x. Not always, but usually. So I'm going to multiply 0.4 to both sides, take the square root, and that leaves me with an x value of 0.00000. So that's 5 zeros after the decimal place, 784 molar. So a very small amount is what x is equal to. Okay. Now it wants me to solve for the pH, and so x is equal to this OH concentration down here. So I have a couple of options. I can either convert this to hydronium, or I can go ahead and just plug it in to solve for POH, and I think that's probably the easiest way. So when I solve for that, the POH is going to be 5.11, but the problem asks for pH, so we're going to use the POH plus pH is equal to 14, and we end up getting a pH of 8.99, which makes sense because we're talking about KB and the conjugate acid, the conjugate base being the sodium benzoate, which should suggest it would have a basic pH just slightly. Okay, so that's how you solve this problem when you have a salt. So when you have the conjugate base or the conjugate acid salt present. Now on lesson 20, we're going to introduce a few things. One is the common ion effect, Lewis acids and bases, and then we're going to start talking about buffers. So the common ion effect, we're still in chapter 14. First, we have to talk about what it means to be a Lewis acid and a Lewis base. So if you remember, we have now the Arrhenius definition, and we have the Bronsted-Lowry, and now we have the Lewis acids. So the reason why the Lewis acid definition comes along is because not all acids and bases swap hydrogens or protons. So there is another group, which is from G.N. Lewis, offered this new definition about what's happening with electrons. So in this case, a Lewis acid is going to be a substance that accepts a pair of electrons. Okay, so a lone pair. Whereas a Lewis base is going to be a substance that donates the electrons, the lone pair. So just like in redox, remember we think of redox equations where electrons are transferred, this is very similar. Now, we have an example here of acids and bases, and we're asked to define. We do know that the ammonia here, we've seen that we could define that as a as a base under the Bronsted-Lowry definition, but we want to make sure it still counts. So in this case, if we're comparing what's on the left to what's on the right, we can see that there's a new bond that's formed. And remember, this bond is worth 2 electrons. So in order to determine where the bond is from, we need to look at the structures on the left. So lo and behold, there are 2 electrons, a lone pair on this nitrogen. And those are the same 2 electrons that form the bond on the right. So in this case, ammonia is the electron donor, making boron the electron acceptor. Because before, when it's a reactant, boron only has 1, 2, 3 valence electrons, but as a product it has 1, 2, 3, 4. So it had to accept an electron in order to do that. So that makes the ammonia, the one that donates, makes it the Lewis base, and that means by definition the boron must be a Lewis acid. Now this bond right here, we're going to call that a Lewis acid base bond, often called an adduct, ADDUCT. Okay, so if we look down here, we had cadmium 2+, and then 4 iodide ions to form this compound. Well, if you can think about what the 2+ means, these are usually things that are electron deficient, whereas the minus means electron rich. So we're going to guess that these are probably the electron donors because they have the negative charge right here. And the 2 plus suggests that the cadmium is electron deficient and in need. So we're going to call that the electron acceptor, which makes this the Lewis acid and makes that the Lewis base. There is this website right here. If you would like more information about identifying it, I suggest you use this PDF through Georgia Tech to look at more examples. So what is the common ion effect? Well, first it's going to be similar to Le Chatelier's principle, so shifting right and shifting left. And it's because we're going to affect the position of equilibrium, so left and right, based on the presence of one or more of the products or reactants already in solution. So we're basically taking something that's at equilibrium, adding more, and disturbing the equilibrium. So it says if you have both benzoic acid and sodium benzoate dissolved in the same solution, what would be your common ion? So what do they have in common? Well, what they have in common is C6H5COO minus, right? We can see in benzoic acid, everything but the proton at the end is common, and on the right-hand side, everything but the sodium is found in benzoic acid. So that's what they have in common. So when we hear common ion, it's what they have in common. And what they have in common is going to be what influences the position of equilibrium. So how would the presence of this common ion affect the pH of the solution compared to one made of only benzoic acid? So meaning how would the pH change if I have a mixture? Well, so let's see. If I have C6H5COOH plus water, and that leaves me with sodium, the benzoate ion and the H3O plus. In this case, this is the contributor to pH right here, right? And so if I add more benzoic acid, the reaction is going to shift to the right, meaning more H3O plus, meaning the pH lowers, becomes more acidic. If I add, let's do a different color, more sodium benzoate, well, now the reaction is going to shift left. It's going to consume some of the H3O plus, and the pH is going to go up. It's going to be more basic, right? Because if we think about plugging it in to the equation, the negative log of, the only thing we plug in there is this. So that's why the presence of both of them influences. And Le Chatelier's principle is the driving force, whether or not it's shifting left or shifting right. So this problem right here says calculate the pH of a 0.4 molar solution of benzoic acid, and it gives us the Ka is equal to 6.5 times 10 to the negative fifth. So let's set up our equilibrium expression. I'm going to add it to water because that's where all of our acids and bases are dissolved in, if you remember back to our general expression. It's an acid, so it's going to give up its proton at the end. Just said that and didn't erase it. And that's going to leave me with hydronium, which is the pH contributor. No water. I'm starting with 0.4 molar, none of the benzoate, none of the hydronium. Reaction's going to shift to the right, just like always, because there is no products and the reactants need to be consumed to produce the products. So we'll subtract from the left and add to the right. Now in this case, my Ka value is going to be, if I want to check to make sure that it's less than the starting amount, it is indeed less than, which means I get to remove that negative x. So now I have Ka is equal to the products multiplied by each other divided by the reactants without the minus x, set that equal to the Ka, and when I solve out everything, x is going to be equal to 0.0051 molar. Now the question asked me for the pH, so I'm going to go ahead and plug that into the negative log of, because the X is equal to the hydronium concentration, so I don't have to do any other calculations, and I get a pH of 2.9. I don't have to convert to hydroxide or POH or anything else like that. Okay, so this is same old, nothing new here. Okay, so same old, same old. I think it's supposed to be same old, but I don't know. Looks like Olay. Okay, so the next one is going to be very similar sounding, except for now it says we're going to have a mixture. Okay, so I'm still going to have benzoic acid, and I'm still going to have the benzoate ion and the hydronium. Except now, initially, I'm going to have 0.4 molar of the benzoic acid, and instead of having 0 on the right-hand side for benzoate, I have a starting amount. But I still have no hydronium. So even though now I have 2 starting amounts, my reaction is still going to shift to the right because I don't have any hydronium, and I can't have a pH if I have no hydronium. So it's still going to consume the reactants, produce the products. Oops. Still going to be the same. And now I have to determine whether or not I can exclude the values. So, sorry, my kid is smacking the bed with a pillow, being very distracting. And so, because if you remember up here, we solved for this, and it was much less than 0.4. Well, if it's less than 0.4, it's still going to be less than 0.2. So what that means is I can get rid of both of these, because the rule doesn't matter if it's got 1 or 2 plus X or minus X. All that matters is if it's less than, then it's negligible. So I'm going to go ahead and set up my expression. I have Ka. Now I have 0.2 times X because my equilibrium values are not just X and X. And the reactant is going to be 0.4, which was the same as the last one. My Ka value is the same. And when I end up solving for X, I'm going to get 0.00013. Now, if you had gone through the trouble of doing the quadratic, and you're wondering what the difference would have been, like say you didn't mark out these X's, the value that I got was 0.000135. So it's such a small difference, and you're saving yourself a lot of time. Now it wants to know the pH, so I'm going to plug this into the pH is the negative log of, and you're going to get a pH of 3.87. Okay, and so the reason why is because that the pH is lower, so more basic than acidic, is because we're starting off with a certain amount of the benzoate ion, so the reaction is not going to lean as far to the right, meaning it's not going to produce as much hydronium, meaning the pH is not going to be as acidic. So because we're decreasing the amount of H3O plus, the pH is more basic. Okay, so that's the effect of starting with a certain amount. The reaction doesn't go as far to the right as it would have, meaning the pH is 3.8 versus the 2.29 that we saw above. So the common ion effect will work exactly the same way with the base and the salt of a base. So it doesn't have to just be something acidic and its conjugate base. It could be a base with a conjugate acid. All right, so what this brings us to now is the topic of buffers. And buffers are going to be super important. You're going to see a whole worksheet on just buffers in just a few lessons or two. And so what is a buffer? Well, a buffer is a solution that has the ability to resist changes in pH, meaning if I add something that's a common ion, then it's going to not fluctuate the pH very much, meaning it's not going to go from 2.29 to 3.87. It's going to go like 2.29 to 2.31. Very small changes. Now, buffers are made out of something very specific. It's making a solution of a weak acid or a weak base and its salt. Okay, so it must be a weak acid, weak base, and its salt. Cannot be a strong acid or a strong base. Okay, so if you were given an option like which of the following can or cannot be a buffer, if there's a strong acid and a strong base present in any of the options, it's not an option. It must be a weak acid or a weak base, and then it's salt. So it has to have that common ion like sodium benzoate and benzoic acid. So there are two important biological buffers. They're here. You have the phosphate buffer, which we actually used a few weeks ago for clock reactions. And this is your internal fluid of your cells. And then you have the bicarbonate buffer, which is present in your blood plasma. So these are all things that help with homeostasis, maintaining a balance in your body, and you have buffers in your body to accommodate for the addition of anything acidic or basic that's not meant to be in your body. And even though your body is made out of water, water is not a great buffer in itself, so we have buffers present in solution to help protect our bodies. So how does a buffer work? So let's take the phosphate buffer that we see above and answer some questions regarding the buffer. So the first one says, using the buffer system above, describe what would happen if strong acid was added. Well, so if I'm looking at this reaction right here and I add a strong acid, I'm essentially adding H plus ions, okay? So which side has H plus ions? Well, the product side does, right there. So if I add H plus ions, it is going to react with the other product, the HPO4 2-. This will shift the reaction to the left. Therefore, all of the acid is consumed. Okay? So what would happen if strong base was added to the buffer? Okay, so when we're adding a base, we are looking at OH. Okay, so if a strong base is added, we're adding OH. Well, if we're looking at the reaction above, we know that OH loves to react with H plus to produce good old H2O. So it will react with the H plus in solution to form water. Now, in Le Chatelier's principle, we talked about when something decreases. So if OH is reacting with the H plus, it's essentially removing it from the equilibrium. And when we remove the H plus, this is going to cause the reaction to shift to the right. Which is the opposite effect of what we saw above. So this consumes the base. Now we know that even though the H plus and the OH are reacting with each other to form water, that because this is neutral, essentially there's really no effect on the overall pH. Okay. Now, there is a specific term which says that the amount of base or acid that a buffer can absorb is without drastic changes, meaning those small changes. It's called the buffer capacity. and all buffers have a limit to what they can take. And so your biological systems also have a limit in your homeostasis, the ability to maintain buffer. So it's important when you work with buffers to know what the limit is, and for your body it has a really important effect because of toxology and pathology and microbiology and all the fun things you'll learn outside of a chemistry class. Now with buffers, we get to treat them just like a common ion problem. But to simplify the calculation, we get to use what's called the Henderson-Hasselbalch equation. And so, back when we learned PivNert, and I told you you're going to see PivNert over and over and over again, well, you are going to see the Henderson-Hasselbalch equation over and over and over again. When in doubt, if you have a buffer and you have a problem like we're going to see, use the Henderson-Hasselbalch, okay? You do not have to use the ice table. However, you could do ice tables with buffers just like we've been doing all along, and you'll get the same answer. So if you like the ice table method, just stick with the ice table. It will always get you to the final answer. If you can determine that it's a buffer problem, and you can figure out that you need to use Henderson-Hasselbalch, then go ahead and use the Henderson-Hasselbalch. Now, the nice thing about this equation is that we use the x is small approximation. So it's not complicated, right? No quadratic, yay, hey. And we have two different versions, if you will, of the problem. So we have the pH is equal to the pKa of the log of the conjugate base over the acid, and the pH is equal to the pKa of the log of the base over the conjugate acid. Now, essentially, this is just products over reactants. Even though we don't necessarily write that in there, it's still going to be products over reactants. So when we think about our general expressions of an acid that we wrote back in lesson 17, it's products over reactants, A minus over HA. And so the way that I remember the Henderson-Hasselbalch, I don't know why this always stuck with me or who taught this to me. Let's erase that. Is that it's aha. Like, aha, I figured it out. So pH is equal to the pKa plus the log of aha. Now, the opposite is the base and the conjugate acid. So if we think about base plus water, HB plus and OH minus, well, in this case, it's going to be the POH is equal to the PKB. That looks all very awful. PKB plus the log of Hubub. I don't know. I can't think of another one. Hubub. Now, the version you see right here of this equation takes everything that I just showed you, the POH plus the PKB, the log of whatever, and puts it into a form that rearranges where you solve for pH. However, I would suggest you not remember that. I would suggest you keep it very clearly an acid, very clearly a base, and that way it's straightforward. Okay, so I would know you need to know these two equations. Now you might be asking yourself, what is pKb? Because I've heard of Ka and Kb now, and I've heard of pH and POH, but I have not heard of pKb. But the nice thing is you solve for pKa in the same way you solved for pH, with the negative log. So to get pKa and pKb, I'm going to take the negative log of the Ka or the Kb and get the answer. Okay, so this is identical to pH. All right. So let's practice some buffer problems because buffers are going to be very, very, very important to us. So in problem number 9, it says to calculate the pH of a buffer, HH, made from a certain amount of acetic acid and a certain amount of sodium acetate, and we're given a Ka value. So pH is equal to pKa plus the log of AHA. Now, you might be asking yourself what the advantages of remembering AHA are. Well, in this case, I can very clearly see that's that's HA, HA, and that this is going to be A minus. And so I know where I'm supposed to plug those in. So now it's a simple plug and chug. Instead of solving for pKa first, I'm just going to plug in the negative log of right here, make myself, save myself a little extra time, or space, I guess. And I'm going to plug in the values of the concentration as they show up in the problem given. So when I take the negative log of the Ka, I get 4.74. And when I take the log of my AHA, I'm going to get negative 0.62, which means my pH is going to, or my pKa is going to, well, I'm not going to say that. Never mind. My pH is going to be 4.12 of what I'm starting with, okay, of my buffer. Now, let's see what happens when we change the buffer. So in this problem, it says, using the same buffer above, what would be the new pH if this many moles of HCl were added to a 1 liter solution? So in this case, I have to convert everything to moles or convert it all to molarity, but fortunately for me, because this is moles, up there is in molarity, but it's all in 1 liter, so there's really no need to convert all of them because it's in 1 liter. If it was 500 milliliters, anything other than 1, I would have to worry about it. But I can assume no change in volume because essentially this is diluting to some small degree, but I get to assume that there's no change. So because I'm changing my buffer, I'm going to need an ice table. It's acetic acid, going to sodium acetate with the presence of water, which when the acetic acid gives up its proton, it forms acetate and hydronium. When I look at my starting amounts before, I started off with 0.24 moles or molarity, and I started with 0.18 moles or molarity. And I started off with none of the hydronium before, but this time I'm starting off with a little bit of HCl, which are protons. So I'm actually going to start off with 0.1 moles of H plus because of the strong acid. Okay. Now, when I add something on the right, we said before up here that adding a strong acid, it's going to react with the salt on the other side, the conjugate acid or base, which is going to shift the reaction to the left. So it's going to shift it to the left by that same factor. We know that it's going to be 100% consumed because that's what it means to be a buffer. Okay, it's going to get consumed 100%, leaving me with none at the end. Once equilibrium is reached, it's going to leave me with 0.10 less of the acetate and 0.10 more of the acetic acid. Now I have a new AHA value. So I can plug this back into my Henderson-Hasselbalch. My Ka is still the same. That will not change. The only thing that's changing here are my values in my AHA. So let's make a prediction before we solve for the answer. I had a strong acid. The equilibrium is going to shift to the left, but there should be ultimately no real change in the pH. And in fact, when I solve for the final answer, I get 4.11, which agrees with my little to no change. This is the point and purpose of a buffer. If you had solved for this at some point and got 8 point something, 6 point something, be very concerned that something has gone awry in your problems. Okay? So let's see. We are about, it should be about 35 minutes worth of lecture. So that should be enough. What I want you to do in the meantime is go to lesson 22, which is a buffer worksheet. And I want you to work on these problems because normally, sometimes we do these in class, but this year we're probably not going to do them in class. But I would like for you to practice them, and then I will post the answers to the problems and maybe go over just a few whenever we return from the break. Okay, I will post other videos to help us answer any questions that we might have with some of the resources like Khan Academy or YouTube that I think are good sources. But please email me if you have any questions that I can help with. We're going to start on lesson 21 for the next lecture, which will be your Friday lecture. Okay,